Okay, guys, quiet down. Quiet down.
Quiet down, Sean.
I have several handwriting, so I just have to choose between them.
All right, 37 minutes. I'm going to go over two examples from this page, and then you'll notice that we're pretty much done with the problem set. So we're gonna have a quiz pretty soon here. So make sure if you've fallen behind that you rectify that.
Don't worry.
Okay, there's a function. When you see a function, it's you always want to look at things like what's the domain of that function? What kind of numbers can go in? What numbers can't go in? So what numbers can't go into this function? Yes. You can't plug in 1, but you also can't plug in -1. And what do we usually want to do when we have a term like this? We want to factor it. But before we factor it, here's some food for thought. If I were to plug in -1, what's the top? -2, and what's the bottom? Okay, -2 over 0, that tells us there's going to be a vertical asymptote. Plug in 1, you get 0 over 0. Oh, that's weird. So plugging in 1 gets us 0 over 0. This is a big thing in mathematics, is what happens when you get 0 over 0.
You can't divide it.
Right, so just the simplest answer to what is 0 divided by 0 is just, it's undefined. So in a vacuum, if there's no context, the answer to 0 over 0 is just undefined. But with some more context, like here's some context right here, in the context of a function, you can actually get some interesting answers. So watch what happens here. The top is, I'm going to write the top. You might see why, maybe not. I'm going to write it like this. Everyone's cool with that factorization, right? Mm-hmm. So now just factor the bottom. Now what do you notice? Yeah, you can cancel-y-wancel-y. That's nice. Oh, beautiful. By the way, that's just like how fractions work, right? Say I had 1 times 3 over 7 times 3. You can cancel out the 3's, right? You have 1/7. So it's the same thing you do with fractions. And just, if you have numbers inside a fraction, it works the same way. Oh, wait a second. Look what you have left over. You have 1 over x plus 1. Now this symbol, I think you've all seen this symbol before. That is the equal sign. It means something. Exactly. It means that this is the same as this. But wait, those are not the same right now. Because am I allowed to plug in, and actually the whole chain of equal signs really. Am I allowed to plug in 1 into this? No, because I'd have 0 over 0 and that's undefined. Can I plug 1 into this? Okay, so obviously they're not equal. So I got to fix that. I got to go, oh, okay, I got to make it so that this guy is the same as this guy. So I have to add in this condition, this domain restriction as we call it, that says x can't be 1. Now they are the same. Okay, this fraction is equivalent to this fraction if you include this extra condition. How are we feeling so far? Does this make sense? Okay. So now we graph. Hopefully we all know what that looks like by this point.
Yeah.
This graph, it's the 1 over x function shifted left 1 unit. You pen users are going to want to be careful on this one, so I'm going to have to go back and fix that.
I switched the pencils.
Yay! So there's my graph, but there's a problem. There's a rule here that says x can't be 1. So that's where the hole is.
What? I've never seen that. No.
Yes, you have.
It can't be true.
You just saw it like 5 seconds ago. The Matrix. Great movie. Great classic. So let's talk about why that is happening. Okay.
Oh my god, I wasn't even serious.
Suppose for a moment that you were to plug in a number into this function. I'll do this in red. Let's say that you plugged in negative 0.9999. Let's just do 4 nines.
That's 2 now.
What kind of y value? If you plugged in negative 0.99999, what kind of y value would this produce?
Pretty nice.
It would be very close to
Pretty nice. Big boy.
But do you get a huge y value? Right? Because you'd be over here on the graph.
Yeah.
Now that's because the way division works is you'd have, because these cancel out, you'd have 1 divided by 0.0001. Really tiny denominator, right? That would produce this large y value. That's what an asymptote is. Hopefully you understand those. We've been covering them for a while. But Sarita, I think this is where your mind was going. If you were to plug in a number very close to 1, positive 1 though, yeah, this number would be negative 0.0001, and so they cancel out. And what kind of y value would we get if this x was awfully close to 1? Yeah, that would get us a y value very close to 1/2. Okay, so that means that this whole, well, the whole, if we're talking about the whole, is actually a lack of a point. It's a gap, so we can say that the whole is precisely at 1/1/2. Now, so then think about that. Do you have to do this whole line of reasoning every time? Of course not. There's a very simple method. What's all I got to do to figure out where the hole is on a graph? If I know there's a hole, I just got to plug in the forbidden value into the function, right? So that's all you got to do.
That makes sense.
So let's just recap the whole process real quick. You have a function. You notice that one of the numbers. Oh, no one told me.
You did.
Oh,
sorry.
I said it when you wrote it.
Sorry, I didn't hear you.
Well, I wrote it on
Oh
my
yeah,
paper
the
without
domain x
thinking
can't
about
be 1 or -1. If one of those numbers, though, one of those restricted numbers, produces a 0/0 in your function, that's a big hint that there's a hole there. It's not 100% of the time, but it's a good percentage of the time. So if you have that, then you factor, look for some cancely-wancely action, and then make sure that the term that got cancely-wancelied, you still retain that domain restriction in your final simplified version. And then to figure out the whole, you just plug that forbidden number in and see what you get. And then to graph it, you just graph this and put a hole where the hole is. Does that make sense? So if you trace this graph out, does this graph have a point at when x is 1.001? Sure, it's right there. It's going to be slightly less than 1/2. What if x is 0.999? Sure, the y value would be slightly greater than 1/2. But is there actually a point on this graph when x is 1? No, there's a hole there. It's like a gap, a void in a function. Okay. Let's do one more example together, and then you'll have some class time just to work. Make sure you understand it yourself. Okay, look at B. Maybe get us started on it while I'm erasing. I hope we all agree that the first step on this one is to factor. Yes. Look at the top. You can factor that.
Yeah.
Okay, so on B, wanna. All right. Hope there's no confusion on the first step. Thank you. the top needs to be 3 times x minus 2. So of course, our domain is all numbers except for 2, but we notice that if we did plug 2 into this, I'd have 0 divided by 0. So again, that tells us we're looking for some kind of hole structure on the graph. Cancely, bobancely. Okay. What's left over? X plus 3. But we still have this restriction. Again, if someone just saw this, they would say, oh, that's a straight line and the domain's all reals. Nope, you gotta add that in because that's still, it kind of inherits that domain restriction from the original graph, or the original function, I should say. This is a little bit easier to graph, right? You all know what x plus 3 looks like. There's your 1, 2, 3. Where's the hole?
2, 5.
If you do plug 2 in here, you get 5, so the hole is at 2, 5. Pretty easy, right?
It looks like a poppet here.
Looks like a what?
Poppet.
A bop it? Oh yeah, twist it, bop it, turn it. Fun game, I guess.
It was.
All right, guys, that's it for the video. Hopefully that was clear enough. All right, guys, I'd like you to try